All right, the last thing we're going to talk about this week, we're going to relate now free energy to the equilibrium constant. And we've already kind of started to talk about this, like which side of the reaction is favored? How do we push this reaction to products, right? We want the reaction to go one particular direction. We've talked about that with regards to equilibrium constants, right? If equilibrium constants are less than one, that tells us that it favors reactants, right? If equilibrium constants are greater than one, that tells us that it favors the products. We've talked about this with Q. If Q is greater than KEQ, right, that means that the reaction is going to go from products and create more reactants. If Q is less than KEQ, then that means that we're going to go from reactants to products, right? So we've talked about it with KEQ, we've talked about it with Q, and we've talked about it with delta G. So delta G less than 0 means that the reaction is spontaneous, and so it's going to produce more products. If delta G is greater than 0, then of course the reaction is going to produce more reactants. And so we're going to bring all three of those things together, KEQ, Q, and delta G today, and we're going to figure out how we do that and what that looks like. Okay, so to do that, we're going to talk about the standard Gibbs free energy. Now, the standard Gibbs free energy is one of those concepts that feels like it should be really important. Delta G like that, delta G 0, right? It feels like it should be really important, and it is because we can actually get a value for it. If we know how much free energy each of the parts of our reaction have, starting materials and products, we can figure out the standard free energy for our entire reaction, right? Is it actually useful? Not exactly, because the standard free energy doesn't actually tell us anything about our reaction, except does this reaction go spontaneously at 0 degrees Celsius, right? So this, what the standard Gibbs free energy represents is, standard Gibbs free energy is the change in free energy at standard conditions. Right? So standard conditions are 1 molar concentration of everything, 0 degrees Celsius, and 1 atmosphere of pressure. Now, we don't run most chemical reactions under standard conditions because, right, 1 molar concentration of everything, that's not every reaction. So standard free energy doesn't really apply too much to actual chemical reactions, but we can get there, we can get to actual reactions from the standard free energy, right? So usually this is something that you can look up or calculate, right? If you know the standard free energies for all your for all the parts of your reaction, you can take the delta G naughts of all your products minus the delta G naught of your reactant, right? And if you add up all your products and subtract all your reactants, you'll get the delta G naught of reaction. Very rarely do we actually do this. Instead, what we do is we say delta G, so this is a non-standard, right? So this is delta G under any other conditions, is related to the standard free energy when we add in RT times the natural log of Q. So what's Q, right? Q is our reaction quotient. So remember, reaction quotient is the concentration of our products divided by the concentration of our reactants at any point in the reaction, right? So if we know what the temperature is, right, the temperature might not be our standard conditions. If we know what the concentrations of our products and reactants are, they might not be the concentration that it is at standard conditions. We can convert the standard free energy into delta G under whatever conditions we're setting up, right? The actual derivation of this formula is another one that's just super, super math intensive. So take some physics if this is the kind of stuff that you really want to know. There's a whole bunch of physics. Take some physical chemistry, and you'll actually derive this from the state functions and all that other stuff. I'm not going to do that mostly because I think I would just confuse everybody, including myself. So I'm not going to do that, but it can be done, right? This is a true statement in this equation, but think of it as we're just adjusting the conditions to match whatever our conditions are. Okay, in this case, R is of course going to be, R is our gas constant, right? R equals 8.314 joules per mole Kelvin, and temperature is in Kelvin, right? So we need to convert our temperatures to Kelvin and all that other good stuff. Okay, so what does this tell us? If delta G is less than 0, right? So if we calculate this out and this is less than 0, then the reaction goes from reactants to products. Reaction goes reactants to products, right? It's favorable to create the products in our reaction. If delta G is greater than 0, of course, the opposite is true. Then the reaction goes from products to reactants. Now, we have before talked about other thermodynamic values that tell us the same thing, right? And one of those thermodynamic values was Q. So if we compare Q to KEQ, we can also say this reaction will go from products to reactants or reactants to products. So real quick, I'm just going to write that back in here, right? So this is also true if Q is less than KEQ, right? And this is also true if Q is greater than KEQ. So if Q is greater than K, then the reaction goes in the reverse direction, products to reactants. If Q is less than K, then the reaction will produce more products. Same thing for delta G less than 0, delta G greater than 0. So basically what we're doing on this slide is we're taking these two different facts. The relationship between Q and KEQ tells us one thing, and the value, the sign of delta G tells us one thing. And sometimes those two things tell us the same thing, right? If Q is less than K, and if delta G is less than 0, delta G is negative, they both mean the same thing. So what does that tell us? That tells us that we can relate these two things. We can relate Q to delta G, and we figured out what that formula is. The last thing here is what if delta G equals 0? Well, that's when Q equals KEQ, because that's when you're at equilibrium, right? The reaction is going neither direction when delta G equals 0, and so we're at equilibrium. What happens to Q when we're at equilibrium? Q is KEQ. So this is important because now we can make this equation even simpler. So let's plug in, oops, I left off my RTs. RT ln of Q. Let's plug in 0 for delta G, and let's plug in KEQ for Q. So if we put the equilibrium constant in here, we know that delta G is going to be 0. That means that we can now solve for the free energy, the standard free energy of our reaction. And we're going to put a negative over here. Negative RT times the ln of KEQ. This is the one we're actually going to use, right? This is how we actually calculate the standard free energy, is we take it from, sorry, forgot I switched my camera. We actually take it from the equilibrium constant, because we can figure out the equilibrium constant. We let our reaction reach equilibrium, we measure the concentrations, and now we can figure out free energy from there. Okay? So we're going to continue to do this, and now what we're going to do is we're going to take this. We talked in the previous video about figuring out delta G for electrochemistry. That means that we can take the cell potential that we calculated in the last video, calculate delta G, and thus calculate KEQ from there. And we can relate all of these things, everything we've done basically this entire semester, KEQ, Q, delta G, cell potentials are all related across one formula. and it's the one that we just wrote down, right? Delta G naught equals negative RT ln K. So we did it. We're almost done. There's not much left to learn at this point. We've tied everything together. So stick around. Next week, we will just dive a little bit more into that equation. We'll learn how we relate this to the cell potentials, and that'll be it for this unit. So thanks, and I hope you have a good week.